Okay, previously, we talked about Stokes theorem and how that's just closely related to Green's theorem. You got circulation on the interior of a region, and you got the circulation around the region, okay? Stokes theorem, you got the circulation around some region and some decently behaved, but could be really wild surface bounded by that curve, okay? And you relate the two integrals, the normal component of the curl over the surface to the circulation, that is line integral f dot t around the, around the boundary, okay? Now, divergence theorem. I don't know if this thing's turning itself or what. I mean, I know it's not turning itself. I'm not sure how it keeps getting turned. Okay. Divergence theorem relates the divergence, which is del dot f for vector function. That's just a scalar quantity that you can integrate over the volume. Okay. So easy to calculate del dot f. It's not a big deal. And if you can set up a volume interval, and that's something that there's still some challenge on. We'll try to address some of those issues next week, okay? Keep working at being able to describe these regions. In any case, that's equal to the integral of f dot n over the surface that bounds that volume. So whereas with Stokes' theorem, you had a curve bounding a surface, here you have a volume bounded by a surface bounding a volume, okay? There's a kind of a similar feel to it, but they're very different theorems, and they measure different things because divergence and curl are two, well, if you have, well, I don't want to make that analogy, forget it. Okay, so the challenge here is first recognizing that you can apply the theorem and then setting up these integrals. Okay? Volume integrals are tough enough, surface integrals even tougher. So you got to get that stuff down. So I'm going to just start with a simple example. That's just a radial field. Now we used a radial field with Stokes' theorem. That if you got a radial field, you pretty much get zero if you try to integrate around a circular boundary in the plane. Okay, so kind of a similar function. I think the function we used with Stokes' theorem divided this by its magnitude, so it was a unit vector field. Okay, I'm not going to bother dividing this by its magnitude. It's going to work just as well as it is. Okay. The surface is the unit sphere. Now, there are various ways to parameterize it. when you parameterize a curve, closed curve or any curve, it's a one parameter thing because a curve is one dimension. Okay. When you parameterize a surface, as you should be aware by this point, you're going to use two parameters. Okay. You want to parameterize a three-dimensional volume, you're going to need three parameters. Parameterization we use is x equal, I was right, almost writing a mu, u cosine theta y equals u sine theta. I'll write out the parameterization again with all the conditions. Theta is going to go from 0 to 2 pi. See, for a given u, you have a circle of radius u centered at the origin. And that should be totally familiar. Okay. It's one of the most foundational parameterizations there is. And I've mentioned that before. So make sure you understand that. Then what's z equal? You got to have z in terms of u and theta because you've already got two parameters. You better be able to express z in terms of those parameters. Well, you solve this thing for z, you get z equals, well, you get z squared equals 1 minus x squared minus y squared. So z is the square root of 1 minus x squared minus y squared, right? Well, when you substitute u cosine theta and u sine theta for x and y, you end up with 1 minus u squared cosine squared theta minus u squared sine squared theta, which is 1 minus u squared times cosine squared theta plus sine squared theta. That part is just 1, and you end up with 1 minus u squared. Now, I'm not going to write that out for you. I recommend that you write this out, fill in the dots, and make sure you see that, okay? Because that's, again, something that comes up again and again. You got to recognize it when you see it, okay? Okay, so again, the parameterization, theta goes from 0 to 2 pi. U goes from 0 to 1. Now, just a little picture that mimics a picture I've made before. This is a bunch of circles. Your U equals 1 circle. Use the boundary here. Now, this might be the U equals 0.2, 0.4, 0.6, 0.8 circle. If you do all the circles for U from 0 to 1, you get the whole disk, every point inside the circle of radius 1. If you then raise up to the square root of 1 minus u squared, come out of the plane up to 1 minus square root of 1 minus u squared. You get surface of a sphere. And actually, and this is what I wanted to do, I said the surface is the unit sphere. It's the unit sphere above the XY plane. So you can put all that together. So we're just using the upper hemisphere. Okay. Plus the unit disk in the XY plane. Because the upper half of a sphere doesn't bound a volume. Now, the whole sphere would bound a volume, but the upper half doesn't, because the upper half is bounded by the unit circle. Okay. That's kind of thing you can use Stokes' theorem on if you've got an application. Okay. But it's not a surface bounding a volume. Now, if you put a cap on it, in other words, take the unit disk, which is everything inside that unit circle, then you have a closed surface. Makes sense? Cut a basketball in half and it's open. Okay. Glue a piece of cardboard over it and it's closed. And you can apply the divergence theorem to any function, vector function inside and on the surface. Okay. All right. So what we want to do is, well, let's finish describing the hemispherical part of the surface. And this is a hemisphere. Your R vector going to be xi plus yj plus zk, which is u cosine theta I plus u sine theta j. Plus the square root of 1 minus u squared times your k vector. You want to find your surface area increment, okay, with a normal vector. So you do RU, or R theta, sorry. R of R with respect to theta is just negative u sine theta I plus u cosine theta j. The k component has no theta dependence. Okay. For given theta, it's always the same. Having forgiven u, it's always the same. Okay, then RU equals cosine theta I plus sine theta j plus, actually be minus u over the square root of 1 minus u squared times k. Now, I'm not going through the details of that differentiation. You need to understand the details of that differentiation. I'm not going to write them up. I'll explain them. It's a chain rule. Now, on the surface, the derivative of the square root of x is 1 over 2 square root of x, right? X to the 1/2 has the derivative of 1/2 x to the negative 1/2. Okay. And that ought to be second nature. If you should have encountered those integrals a number of times by this point of the course, in examples and in problems. But if there's a chain rule, you got to take the derivative of the interior function, which is 1 minus u squared. The derivative of that is negative 2u. So you get negative 2u times 1/2, 1 minus u squared to the negative 1/2. The 2 here and the 2 there cancel out, and this is what you end up with. So check with that, okay? Write it out carefully, because I'm capable of making mistakes, but I'm pretty sure I didn't make one there. Okay. Now you understand where we are in the process. To do a surface integral, we parameterize the surface. And remember, we've only parameterized the upper hemisphere. The unit disk down in the XY plane is going to be easy to parameterize. Now we can actually wave our hands and get that integral without even having to do anything. Okay, but we've parameterized it. Now in parameter space, in u theta space, your surface area integral, your surface area is a rectangle. It's a rectangle oriented in u theta space, not in XYZ space anymore. Okay? So it's like you deconstruct this sphere and map it onto a u theta plane. Whether that makes sense to you or not, this is how you do it. So that r theta cross ru is your ds increment. Well, ds equals r theta ru times ru times du d theta. Again, it should be familiar. And ds with an arrow over it is just normal vector times ds without an arrow over it. ds without an arrow over it, without an arrow over it, is just the area. And ds is the area with a normal vector sticking out of it. Okay. Okay, so we have this. Well, let's calculate ru cross r theta cross ru. You can do this with or without the determinant. If you look at it, you're going to have an I times a J here, I crossed with a J, and an I crossed with a K. You don't bother crossing I with I because that's 0. You have a J crossed with I and a J crossed with a K. So there are only 4 components out of 6 that you need to calculate. So you do that using the distributive law, but since everybody likes to use the determinant, we'll do it that way. Okay, so it's negative u sine theta. I'm going to give myself more room. U cosine theta, 0. And then it's cosine theta, sine theta, and negative u over the square root of 1 minus u squared. Written that kind of small, but something you should be able to do. So it's I times the determinant of this minor. Well, the determinant of this minor is just the diagonal because you got a 0 here. It's I times negative u squared cosine theta over the square root of 1 minus u squared. And then it's j. Well, let's write it out correctly. It's minus j times the determinant of the minor consisting of this part and this part. You know, throw away the row and column of j, and you got the minor. And you're going to get u sine theta times negative u over 1 minus u squared, which is u squared sine theta over 1 minus u squared minus, well, minus nothing, which is 0. Okay, 0 times the cosine. Now, if you look at these, you see you've got the same thing on both of these. My cosine theta should have been squared, and my sine theta should have been squared, sorry. Okay, you got the negative u squared over 1 minus u squared both times, and you got a cosine squared theta and a sine squared theta. Cosine squared theta and the sine squared theta would add up to 1, right? Now, since one is times I and the other is times j, maybe that's not really going to happen. But it's something you want to recognize as soon as you see it. All right, and we'll see if it happens. Okay, then it's going to be plus k multiplied by the determinant of this minor, which is negative u sine squared theta minus u cosine squared theta, and there's no denominator. So let me rewrite it. Over. And that's just u. As the cosine squared plus the sine squared. Factor it out, you get u times sine squared plus cosine squared, which is u times 1, which is just u. Okay, so there's your n ds in this integral f dot n ds. Okay. Now to get the flux through this thing, the component, the total of the f components perpendicular to the surface, the normal components of f, you got to integrate f dot n. And I don't have room here to do all that. So I'm going to come over here. Now, that seems problematic. But we'll see if we can behave. Okay. Now, double integral of f dot n ds. Well, f is xi plus yj plus ck. X is cosine theta, y is sine theta, z is square root of 1 minus u squared, right? So, well, I'll write this out the way you might tend to write it out. It's xi plus yj plus zk dotted with trying to factor something out of this. But the only thing that factors out of all this is u, so I'm not even going to bother. This is u squared cosine squared theta over square root of 1 minus u squared I, similar for j. Plus uk du d theta. Now, what are you going to do with that? Are you going to get x times negative u squared cosine squared theta and so forth? Well, no, you're not going to mix x's and y's with u's and v's. Remember that you parameterized the surface and you're integrating on the surface. So on the surface, x equals a cosine of theta, y equals a sine of theta, u cosine of theta and u sine theta. And z is the square root of 1 minus u squared, okay? So you probably wouldn't write out that intermediate step after you've done a number of surface integrals. You know that you don't need to write it out. But on some papers, I've seen it written out like this, and then it can lead to confusion. So let's write out what we get. We get a double integral of cosine theta I, u cosine theta I, plus u sine theta j, plus the square root of 1 minus u squared k, dotted with negative u squared cosine squared theta over the square root of 1 minus u squared minus u squared sine squared theta. This is times I. Then it's minus u squared sine squared theta over the square root of 1 minus u squared plus times j plus uk du d theta. Now, u goes from 0 to 1, theta goes from 0 to 2 pi. So let's go back and look at it. Okay, u goes from 0 to 1, theta goes from 0 to 2 pi. So if you're subdividing this into u theta rectangles, u has no dependence on theta, and theta has no dependence on u. So the limits on this integral are very simple. This is just a rectangle in u theta space. Okay? So you have very simple limits on the integral. With respect to u, you're just going to go from 0 to 1. With respect to theta, you're going to go from 0 to 2 pi. Okay, and the rest is obvious, right? No. I mean, it's obvious what you got to do. As far as actually doing the integration, it might be a little less obvious. Well, you're going to have u cosine theta times negative u squared cosine squared theta. You're going to get the I components u cubed cosine cubed theta over 1 minus over the square root of 1 minus u squared. It should have a negative on it. And then minus u cubed sine cubed theta over the square root of 1 minus u squared plus uk. That's du d theta. See anything that they can do with this? Well, we have cosine cubed theta and a sine cubed theta, both with negative signs on them. And actually, we can't do anything with that. We should be able to, do I have an error in one of these? Maybe it should be sine squareds and cosine squareds. But cosine squared on the I almost inconceivable. I might have made a mistake when I did this. I did the cross product. Yeah, that shouldn't have been a cosine squared because that came from u cosine theta times u over the square root of 1 minus u squared. There's just one cosine in this. And when you do the j, there's just going to be one sine. So when I got down here, I didn't stop and think. I didn't stop and check myself. It is a wait a minute, there's a u squared, there's got to be a sine squared. Okay. Wasn't thinking about where things came from. So I was careless there, and I'm paying for it a little bit now, but it's going to be easy to fix. All those cosine squareds and sine squareds go away until we get down here, and then we got to do the dot product, and the cosine cubed and sine cubed will be cosine squareds and sine squareds. And now I'm feeling much better because if they've been cosine cubes and sine cubes, I don't think I could have integrated. I might have. It was immediate to see the path to that. But okay. Now the point then is that this minus this, I could factor out the negative u cubed over the square root of 1 minus u squared and just then end up with that times cosine squared theta plus sine squared theta. So I'm just getting a negative u cubed over the square root of 1 minus u squared. And there's no I, j, or k on it because we've done the dot product. I have a k on this thing. Then it's plus u du d theta. And of course, u du is easy to integrate. How are you going to integrate u cubed over the square root of 1 minus u squared? Should be something that's halfway familiar to you from first year calculus. See how much board I've got to work with. Make a little note up here. Let's let w equal u squared. dw equals 2u. 2u du. Which means that one of these u's, of the cube u's, goes with the du to give you 1/2 of a dw. So that u cubed becomes w, which is u squared, times 1/2 dw. Which is, of course, then just do the whole thing. Then the square root of 1 minus u squared becomes the square root of 1 minus w. Sign down here. So we're integrating basically just w over the square root of 1 minus w. Then, and this is basic substitution. Not the simplest type of basic substitution, but it's one you should have encountered a number of times. First year calculus. It's been a while though. Okay. Then we make another change of variable. If v equals 1 minus w, then w equals 1 minus v. So 1/2 of w dw over the square root of 1 minus w equals 1/2 of negative 1/2 of 1 minus v dv over the square root of v. I heard some conversation. They do something ignorant. Okay. Oh, he did. It's okay. It's okay. Now that looks a little bit complicated. You ought to review that just to get the wheels turning on integration, because that is the kind of thing that I might well expect you to be able to integrate. Okay. I'm just going to give you that much of a hint and ask you to figure out the rest of it. I mean, well, okay. That equals negative 1/2 of 1 over the square root of v, which is easy to integrate. You know, integral is 2 square root of v, right? Minus the square root of v, which is 2/3 of v to 3/2. Okay. And you integrate it. Okay, so when you do all this, you build up your integral of this thing. And I'll leave the rest of it to you because I think you need a little practice with the integration. Now, that was all a moderately complicated surface interval. Okay, just moderately complicated. The process is exactly what it should be, but then you run into, some ugly algebra and some vaguely familiar integration. Okay, what I would expect at this point. How else could we have figured this out? Well, we could have integrated del dot f over the volume of this thing, right? Now, also, I've neglected the plane. Okay. But it turns out that in the xy plane, z is 0. Your k component is 0. Okay. So I think I'd better establish that. I better make sure that before I say it. But that one's easy to integrate. Okay. In any case, because the normal component is just negative k. You've got this hemisphere. It's here and then it's flat. On the flat part, the outward normal is straight down. It's flat parts in the xy plane. Downward unit normal is negative k. All right. And that makes it easy to integrate. Still, it's two surfaces. You have to integrate this function over. What about this volume integral? What we want to look at is triple integral del dot f dv over the hemisphere, radius 1. Okay. What's del dot f? There's f. Tell me what del dot f is. Show me with your fingers. Nope. Nice try. You can always hope. Got a 0 there, but that wasn't it. Okay. What else? Hey, you ought to be able to do that in your head if you've done a bunch of divergences, del dot f's. You've been doing most for a while. Well, I'll give you a hint. What's a partial with respect to x of x? Show me. Make sure you're careful which finger you use. Yep. Partial with respect to y of y is, partial with respect to z with respect to z is. So what's the divergence? 3. Okay. Now I'm illustrating that this is much easier to do this than it is to do this in this case. The volume integral is much easier than the surface integral. And volume integrals are in some ways easier than surface integrals because you got to get the surface integral, you got to parameterize and everything. But to get a volume integral, you got to do the limits on the integrations. There it is. It's the integral of 3 dv. R is 1. 2 goes into 4 twice, 6/3. It's 2 pi. I did that quick, so check it. Okay. Wait a minute. Yep. Did it a different way, still got 2 pi. Okay. And if you integrated the divergence over the whole sphere, what do you think you get? 4 pi. Because you're integrating a constant over the volume. Now, if you don't happen to know what the volume of the sphere is, put this in here. If you officially want to do the triple integral, it takes a while to write out these things, but you got the integral from -1 to 1 of the integral from square root of 1 minus x squared to square root one minus x squared minus y squared of the integral and my original impulse is correct. Sorry, I'm not quite with it today. Of 3 dz dy dx. And these are all, you do this by trig substitution. X equals cosine theta. So dx is sine theta d theta. So you got sine theta d theta over sine theta. You got to know those integration tricks. But I kind of leave it to you to review your integration a little bit. We can talk about it next week when we've covered everything. And we can fill in some of the blanks. But try to do some work yourself or you won't be ready. Get that if that's what you choose to, again, we want to review. I'd rather not do a lot of review first semester, first year calculus. Rather you would review that so we can pull together multivariable calculus, okay? If you got to do a little bit, we can. Or I can do a short video that you can have reference to. Of course, you could just Google common integration techniques for first year calculus and review it that way. If you're into something you don't understand, yeah, you're welcome to run it by me. Okay. So, you leave it up to you. Check your integration technique by doing this integration and see if the whole blame thing doesn't just come out to 2 pi. A hint, when you integrate u, you get u squared over 2. Integrate u squared over 2 from 0 to 1, you get 1. Then integrate theta from 0 to 2 pi just on the u, you get 2 pi. So somehow this must give you 0. Actually, I'm having a hard time seeing that. But I worked it out last night. just to see how involved it got. I worked out a little different way. And what I just repeat what I did last night, but it worked out. So if I've got everything down here right, it worked out. And if I don't, you're welcome to fix them. Okay. Okay, that's a good illustration of what you got to do in the surface integral. Also, pretty good illustration of the divergence theorem and how one integral can be much simpler than the other. Okay. And most of your problems are show that this integral is equal to something by doing that integral. Okay. Okay, let's see. Give me a second. Okay, now I don't usually pick examples out of the book, but I wanted to pick one that's fairly simple. Okay. It's the one that we just did, even though it's a pretty simple region to understand, even though it's pretty easy to visualize. Surface integral should be pretty nasty. Not really nasty, but somewhat involved anyway, as they usually do. Okay, so we've got this function, and we want to use the divergence theorem to find the flux of this field through the boundaries of this rectangle. Okay. Now, if we want to directly calculate the flux, we're going to have to calculate the flux on this face and 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 this face. Okay. I think I said some of them too many times, but you get the idea of 6 faces. So we'd have to do 6 surfaces. Now, if there's some symmetry involved, maybe the integral over z equals 1 and the integral over z equals -1 will have some relationship, cuts it down a little bit. But the surface integral would involve at least but would require integration over 6 faces, because you have 6 faces that the flux can go through. Okay. The volume integral ought to be really easy because you've got a cube. Okay. Just integrate x from -1 to 1, y from -1 to 1, z from -1 to 1. And so hesitate to say easy. I say easier, but I think it's going to be easy because everything you got here is going to be just x's, y's, and z's, no powers, no nothing. And I mean, you integrate, you might get some powers. We'll see. Yeah. Integrate the divergence, del dot L equals what? Well, it's going to be 3x I, and I'm just going to write this down without comment, plus 2z a plus xy k. Del dot L. X derivative of this, y derivative of this, z derivative of this. Okay. I've got all the constants there. integrate this over the cube. Well, and have 3xi and 2xj and xyk. When you do the dot product, you end up with a scalar, not a vector, right? I dot I is 1, j dot j is 1, k dot k is 1. Work it out. Do a bunch of divergences until you learn to see it and learn to do better than I do by not putting the i's, j's, and k's in this thing. You do, that gets confusing. Okay. So what we have to integrate then is 3x plus 2z plus xy. And we can do dy, dx, and dz in any order we want. So I just arbitrarily write it dy, dx, dz. Okay. I've written dx, dy, dz, dz, dy, dx, whatever. Limits are the same. Okay, so that'll be the integral from -1 to 1, from the integral from -1 to 1 of integrate with respect to y. 3x with respect to y is 3xy. Integrate 2z with respect to y, you get 2zy. Integrate xy with respect, I said with respect to y. I said with respect to z, but you're integrating with respect to y. Integrate xy with respect to y, you get xy squared over 2. And then it's dx, dz. And this is evaluated between 1 and negative value. So that'll be the integral from -1 to 1 of the integral from -1 to 1 of, okay, well, y goes from -1 to 1, so I'm going to get 3x. You can work out the details. At 3xy, y equals 1 is 3x. 3xy when y equals -1 is -3x. And when you subtract -3x from 3x, you get 6x. Write it out carefully, step by step. This should be obvious at this point, but you know, what should be obvious is not always obvious. So I don't want to explain each of these, and I don't want to take the time to write each one out because you need to. It's a very simple process, and if you're not able to do it easily, you really need to work it out yourself. Okay. Integrating with respect to x, we get 6x and x, and that's going to be 7x. Then we're going to get let's write y equals -1 to y equals 1. Let's write x equals -1 to x equals 1, just to make sure we don't substitute for the wrong variable. Okay. Well, obviously I'm out of room, but I think I can do this anyway. It's integral from -1 to 1 of, now, x squared evaluated at 1 is 1, and evaluated at -1 is 1. So x squared evaluated from -1 and 1 gives you 0. So you get 0 here. And here you get 4z times 1 minus 4z times -1, which is 8z. And you got 8z dz, which is HC squared over 2 between -1 and 1, which is 0. Now, you might have been able to see that the integral would be 0. Actually, no, that would have been a little hard for you to see. I mean, these are basically degree 1 and degree 3 odd degree expressions. This is an odd degree expression, but this is an even degree expression. And if you break this thing into octants, some octants will cancel others out on certain variables. And that's a little more complicated, so I don't want to talk about that. And I'm not instantly saying the specifics of it here. Okay. You just have the intuition that pairs of octants will cancel each other out. I'd have to think about it a little more. So we get 0. Now, if you tried to do the integral of f dot n over one of the phases, just write out a little bit about what that would be. Let's just take the z equals 1 phase, which would be this one. Well, that would be x cubed minus 3yi plus 2y plus 1j plus xyk dotted with what's the normal vector on the z equals 1 phase. Point in the direction of the normal vector on this phase. The cube is like this. So we're talking this phase. That one, right? Well, it's got to be perpendicular. What's perpendicular to this? Okay, it's this. Okay. So your vector would be j. Which equals 2y plus 1. Now, on that face, you wouldn't have to go through a lot of parameterization. Z is 1. So you only have 2 parameters, x and y. They both go from -1 to 1. You don't have to go to the trouble of doing RU cos RV or whatever. You know what the normal vector is. And it's a rectangular region in just x and y. So you don't have to go to any of the trouble we had to go to on the integration over the hemisphere. So the integral of f dot n ds is just the interval from -1 to 1 of the interval from -1 to 1 of two y plus 1 dy dx. That's going to be y squared plus y. Y squared is going to give you 0. Y is going to give you 2. And I think it gives you 4. I might be careless there, so check me on it. Okay? It's very simple. If you did it on the opposite face, the value would still be 2y plus, well, z would equal -1. So this would be a negative xy. This would be a negative 2yz. And I'm thinking you should get the negative of the result here. But looking at the way the signs work, it looks like you get the same result, which kind of contradicts the fact that we get 0. So maybe there's not an obvious way. Looking at the flux, if you can establish that the flux in this direction is opposite to the flux in this direction, okay, then you get 0. And if you can do that over each pair of faces, you get 0. Either I'm getting the sign wrong, which is not unlikely, or there's some other reason the thing comes out 0, or I screwed up the integration, it doesn't really come out 0. Okay? Principle here, though, is if you got a cubical boundary, number one, you got an easy volume integral to set up. Maybe it might not be, depending on the function, it might not be that easy to evaluate, but it's easy to set up because it just has constant limits, okay? You've got 6 faces, but a lot of times there's some symmetry between opposite faces. So you can kind of exploit that. Okay, so you do have, I think in these line problems, there are problems involved cubical regions. Remember, I'm giving you 2 alternative problems for each one. Just another way of helping you prepare for an exam. You really ought to be maybe looking at those alternative problems. Maybe not working every one of them because that'd take more time than you probably have. But looking at them and thinking, what do I have to do this? Sketch it out in your head. Say, okay, yeah, if I can integrate the arctangent of e to the 7x, I can get that, but you can integrate that. Okay? You understand what I mean? You know, just the broad view. And then review the details. You do have to have some integration technique. You have to use your integration technique. And you have to be able to describe regions. All that stuff. Okay? You came up fairly well on the midterm. Wish everybody's grade would have been at least 1 unit higher, but it wasn't bad. Okay? So hang in there and try to do at least as well in the final. Hopefully improve your grade by, but try not to let it go down. Okay? Prepare. You have all of exam week. Unless I say differently. The only way I'd say differently is if the deadline is different. Okay.